Hi everyone, welcome to Etabs 2015 Advanced Tutorial. In this tutorial, we'll be dealing with the time history analysis in Etabs 2015. Time history analysis provides for linear or nonlinear evaluation of dynamic structural response under loading, which may vary according to the time function we define. So, the dynamic equation that has been formed from the time history analysis can be solved by following two methods. The first one is a model method, and the second one is a direct integration method. So, in this tutorial, we'll be dealing with the linear model time history analysis as per ASCE 710. So, in order to save the analysis time, I have come up with a smaller model this time. So, the model that I have considered here is a G+6 building, which is having a total height of 20 meter and the typical floor height of 3 meter. So here, under the define, in define load patterns, I have defined the dead load, live load, and the masonry load, and also the earthquake loads along both X and Y direction. For example, let's consider the earthquake load along the X direction, and I will just show you what are the factors I have defined for the earthquake load. So here, I have applied the direction as X direction plus eccentricity by applying an eccentricity of 5%. And for time period, I have opted for the program calculated, and the story range has also been defined here. And the factors such as response modification factor, the system out strength factor, deflection amplification, and the occupancy importance has been given as 8, 3, 5.5, and 1 respectively. And under seismic coefficients, the spectral acceleration for short period and for the 1 second has been selected as user defined. And the 0.2 second spectral acceleration, that is the SS, has been given as 1.145, and the 1 second spectral acceleration has been given as 0.52, and the long period transition period that I have opted is 8 seconds, and the site class has been selected as D, and with respect to these values, we have calculated the design spectral acceleration, that is for 0.2 seconds and 1 second. In similar manner, I have applied the same factors for the earthquake load that is acting along the Y direction. And after defining the load patterns, I have defined the mass source. So if you can go to the mass source, you can see that I have defined under the mass source the specified load patterns, where I have considered the dead load, the entire dead load, and the 25% of the live load. And now under the define again, let's go to the model cases. So here under the model, I have defined the model case as model and the model case subtype as eigen. And under the P delta nonlinear stiffness, I don't want to consider this, so I am using as a preset P delta settings. And under other parameters, I have considered the maximum number of modes for the time being as 12 and the minimum as 1. So before going to the time history analysis or defining the time history function, let's find the fundamental period of this building. So for that, let's analyze this model. So the analysis is complete right now, and let's find the fundamental time period. So for that, go to the show deformed shape and select the mode. And we have selected the primary mode, that is mode number 1, and click on OK. So here you can find that our fundamental time period is 0.863 seconds. So let's unlock the model here. And now we need to define the time history function. So now let's move on to the first step of time history analysis, that is defining the time history function. So here I have obtained the ground motion data of Imperial Valley earthquake of 1940. So these two are the time history data that I have obtained that I'm going to apply along X and Y axis respectively, and these two are actually separate time history data of Imperial Valley earthquake, and I have obtained this data from the peer ground motion database, and you can visit the following website to obtain different ground motion data. So now go to define and select the functions, and from the functions select the time history, And here in this dialog box, you can see a heading called choose function type to add. And from this drop down, select the from file option and click on add new function. So here we need to define the time history data that we are going to apply along the x-axis. So let's browse for the acceleration file that we need to apply as a time history data. So click on browse. So here in this folder, I have saved the acceleration, displacement and the velocity data files along x, y and z axis. But here for analysis, we are only considering along both x and y axis, and that too only the acceleration data. So the first one along the x-axis is the acceleration data. So I am selecting this one. And after selecting the file, first what we have to do is that under values are select the values at equal intervals of, and if you just view the file, you can see that the entire ground motion points has been entered in a notepad file, and here you can see the number of points and also the time interval period that has been listed here. So we have to input this value of 0.01 seconds at this box, that is at values at equal intervals of. So let's change from 0.02 to 0.01, and then after we have to now change, or we have to edit the values of header lines to skip, prefix characters per line to skip, and number of points per line. But here now we are not going to skip any prefix characters, as our file doesn't have any one of it. So we are going to deal with the header lines and the number of points per line. So now if you're going to view the file again, you can see that our ground motion data lines are actually starting from the fifth line of this notepad file. That is, the first line starts from here. So the first 4 lines are actually the header lines, and the ground motion data starts from the fifth line. So when you plot the function or the time history data, we need the graph to start from the fifth line. So we need to skip the first 4 one. So here we change the header lines to skip from 2 to number 4. And here at number of points per line, I just select the first for the time being. So here when I select the number of points per line as number 1, you can see that the analysis time is about 10.7, almost 11 seconds. But in case if I change from number 1 to number 2 points, you can find that the analysis time has increased from 11 to almost 22 seconds. That is, the analysis time has doubled. But for my time history analysis, I need a short analysis time. So here I settle for number 1, that is number of points per line that I'm going to select is 1. So after assigning all these factors into this dialog box, click on OK. So in the similar manner, I'm going to define the time history function that I'm going to assign along the y-axis. So again, click on add new function. So browse for the file that is having the acceleration data along the y-axis. So the first one is the acceleration data. So I have already uploaded the file, and similar to what I have done along the x-axis, do the same over here. And after entering the data, click on OK. And now let's move on to the second step, that is defining the target response spectrum. So here we have already defined the time history function, and we need to scale or match that time history function defined with respect to a target response spectrum. So for defining the target response spectrum, go to define, and from functions select the response spectrum. And here under this drop down, I have selected the ASC 710, and after that click on add new function. So here I am going to name it as target response spectrum, and here the parameters for the spectral acceleration with respect to short period and 1 second is user specified, and the 0.2 second spectral acceleration is 1.145, and 1 second spectral acceleration is 0.52, and the long period transition period is 8, and the site class is D. So here the function graph that has been plotted with respect to the time period and the acceleration, and we have defined a function damping ratio of 5%. So after defining all the parameters, click on OK. So here we have defined the target response spectrum, and next we have to match the response spectrum or scale the response spectrum with respect to the time history function. So for that, go to define again, and under functions select the time history. So here under choose function type to add, from this drop down select the last option, that is match to response spectrum, and click on add new function. So here under the time history function name, I'm going to name my time history that I'm going to scale along the x-axis as THX. So here under spectral matching, you can see two options that is being given under spectral matching. That is, one is the matching in frequency domain and the other one is matching in time domain. So for now, let's start with the matching in frequency domain, and then we will move on to this part. And here under the target response spectrum, we assign the response spectrum that we have defined before, and the response spectrum acceleration unit is in G units. Under the reference acceleration time history, we define the time history that we want to assign along the x-axis, that is ELC 181, and the time history also is being defined in G units. So here you can see the target response spectrum graph being plotted, and on the right side you can see the reference time history acceleration. So at the start of the tutorial, we have found the time period of a structure. So as per ASC 710, it states that when we scale the time history function with respect to target response spectrum, the values of the time history should be above the 0.2 times the time period to 1.5 times the time period. So here the time period is the one that we have found at the beginning of this tutorial, that is the fundamental model time period, which is 0.861 seconds. So here when we consider with respect to 0.2 times to 1.5 times, the time period that we have to consider here is from 0.17 to 1.29 seconds. So that will be like from this point till this point. So when we match, we must have the time history values more than the spectral or this target response spectrum from here to here. So next we go to the set matching parameters, and let's click on it. And here I select the program determined frequency range, click on OK, and next let's match the time history. So click on match time history. So the matching has been done, and here you can find the blue line corresponds to the actual time history data and the red line corresponds to the matched time history data. But here you can find that certain values from 0.17 to 1.29 seconds are under the target response spectrum, which means that a proper matching is being not done here. So let's try the second method, that is spectral matching in time domain. So here we define as similar to the frequency domain the target response spectrum and the reference acceleration time history, both in G units. And under the set matching parameters, we select the program determined frequency range, and let's keep the time domain spectral matching parameters untouched. Let it be like this itself, and click on OK. And now we click on match time history. So now the scaling of time history with respect to response spectrum has been done in time domain, and you can find that from 0 to 1.29 seconds there is a better matching in time domain with respect to frequency domain. So from now onwards we'll be selecting the time domain as for the spectral matching. So after this, click on OK, and the similar manner we are going to match the time history function along the y-axis that we are going to assign with respect to response spectrum. So click on add new function, and we name it as th y underscore scaled, and let's select the spectral matching in time domain because it gives the better results. And here under the target response spectrum, select the target response pattern we have defined, and the reference acceleration time history, we need to select the time history that we're going to assign along the y-axis, that is ELC 271, and both has to be defined in G units. And here let's match the time history. So here the matching of the time history data with respect to y-axis has been done with respect to the target response spectrum, and we can find a better matching results also here under time domain. And after matching, click on OK and click on OK again. So now we have done with matching with response spectrum for the both time history functions along x and y axis. So next we have to define the scaled time history function as a load case. So for that, go to define, select the load cases, and here click on add new case, and under general let's give a load case name for our time history, that is time h, and the type of load case is time history. And here we are going for linear model time history analysis. So select the linear model from the drop down, and the mass source is being defined here. And here under the loads applied, we have to define the acceleration that we are going to apply in both x and y axis. So click on add, and here select the acceleration, and the load name is u1, and the function is the scale time history along the x axis, and click on add again to define the acceleration along the y axis. So here we select the scale time history along the y axis, and next here we have to fill the scale factor, and the scale factor is Ig divided by R, where I is the impedance factor of the building and G is acceleration due to gravity, which is 9.81 meter per second square over here, and R is a response reduction factor, which is 8. So here we get a value of 1.23. And here if you can just take the advanced box, you could see more options over here like time factor, arrival time, coordinate system, angle. But for this tutorial we are just going with the basics, so we are not including the advanced options. And under other parameters, the model load case is model, and the time history motion type that we are going to adopt is transient. And here I require an output time step size of 0.1 seconds. And as we know that the time history that we have adopted along both axes have a total analysis time of 12 seconds, the number of output time steps will be 12 divided by 0.1, which gives an answer of 120. And here we adopt a model damping of 5%. So here we check the constant damping for all modes, and we give a value of 0.05 here, which corresponds to 5% of damping, and click on OK. So the time history function as a load case is being entered with a type of linear model history. Click on OK here. When you apply the scale factor, the one thing that you have to make sure is that the display unit for the acceleration for the length should be in meter if you're going to apply a scale factor of 9.81. Suppose if you're going to enter a unit of mm, the G value will be 9810, and if the unit is in centimeter, the G value will be 981. So as I am entering my length unit as meter for acceleration, I'm going to apply a G value of 9.81. So next let's analyze our model with respect to the time history load case. So here we have finished analyzing our model. So after the analysis, go to display and select the plot functions. So here you can find in the plot function is that the base year is being plotted with respect to time period, and here you can find that the maximum base year, that is the positive base year, is found at 9.2 seconds, which is over here, and the minimum value of base year is found at 10.5 seconds, that is the negative base year, that is over here. In similar manner, you can find the base year along the y-axis, which I have already defined. So if you just select the base shear along the y direction. Here you can find that the maximum base shear occurs at 7.6 seconds. That is over here, which is having a value nearly to 796. And the negative or the minimum base shear occurs at the value of 4.5 seconds of time period. That is over here. And now let's go to display and select the show tables. And here in results, in reactions, select the base reactions and click on OK. And in load case combo, I am just selecting the EX, EY, and the time history maximum and the time history minimum. So here we have obtained the base shear values with respect to static and time history analysis along both X and Y direction. So next what we have to do is that we have to scale up the time history base shear with respect to the static analysis base shear. So for that, let's consider along the X axis. So here we're going to take the average time history base shear of maximum and minimum, and I'm going to scale up with respect to the base shear that I have found with respect to the static analysis base shear, and here I obtain a scale factor of 1.54. In similar manner, I consider along the y-axis and I take the average value of both time history maximum and time history minimum, and I'm going to scale up this average value with respect to the static analysis base shear that I have found along the y-axis, that is EY. So in similar manner, I found a scale factor of 1.48. So for applying the new scale factor, let's unlock the model. And let's go to define and go to the load cases, and let's modify the time history load case. So here I'm going to apply the new scale factor. So here the scale factor will be 1.89, and along the y-axis the scale factor will be 1.82, and let's click on OK, and let's analyze it again. So the model has been analyzed, and let's check the base shear again. So here we can find that the time history base shear has been almost scaled up to the static analysis base shear along both X and Y direction. So in show tables, you can also check for the model results, that is the model load participating mass ratios and model participating mass ratios, but I'm not going to explain that in detail in this tutorial. You can check the response spectrum analysis video in our YouTube channel Civil Know-How Tutorials, and I have explained very well this part. So now let's click on OK, and now let's find the shear force and the bending moment of the structure with respect to the time history function. So let me check the member force diagram for frames, piers, spandrels and links. And in the case, I'm going to select the time history. I'm going to select the time over here, and let me start with 0.2 seconds, and click on apply and OK. So here in this part you can see this is 0.2 refers to the second step, because in the initial part we have defined the step size of our analysis as 0.1 seconds. So 0.2 will be second step, and let's check the bending moment of this beam. So if you increase the step size or the time like 0.3, 0.4, you can see the variation in shear force and bending moment. And in this way, you can have a study of your behavior of your structure with respect to the time history ground motion. In similar manner, you can also check the values for the drift. As per ASC 710, it recommends to use at least 3 ground motions for the time history analysis study or time history analysis observation. With this, we come to the end of the tutorial. If you find this tutorial useful, please do like and share this video, and make sure you subscribe to our channel for the upcoming tutorial videos.